Magnetism. Satellites sometimes contain loops of wire called magnetic torque coils that a satellite operator on Earth can activate. When current is in the coil, the magnetic field on Earth exerts a torque on the loop of wire. Torque coils are used to align a satellite in the orientation needed for its instruments to work. Astronauts Dale A. Gardner and Joseph P. Allen IV work together to bring the Westar 6 telecommunications satellite into the Discovery Space Shuttle's payload bay. Allen is on a mobile foot restraint, which is attached to the Discovery's remote manipulator system. The satellite had to be recovered because a propulsion system's defect prevented it from reaching a sufficient orbital radius, altitude, for telecommunications purposes. Chapter 19 Overview, Section 1, Magnets and Magnetic Fields, introduces magnets and magnetic fields and discusses magnetization. Section 2, Magnetism from Electricity, applies the right-hand rule for magnetism, explores electromagnetism and solenoids, and introduces magnetic domains. Section 3, Magnetic Force, concentrates on calculations of magnetic fields and magnetic forces. Knowledge to review: a net force causes a change in the motion of an object. Torque is the cause of changes in rotation. The magnitude of a torque equals the product of the force and the lever arm. Electric fields surround charged objects and exert forces on other charged objects. Electric current is the rate in which electric charges move through a cross-sectional area. Items to probe: electric fields. Have students relate electric field strength to the force exerted on a charged particle in a field. Chapter Preview, Section 1, Magnets and Magnetic Fields, is broken into three subgroups: magnets, magnetic domains, and magnetic fields. Section 2, Magnetism from Electricity. Two subsections: magnetic fields of a current-carrying wire and magnetic field of a current loop. Section 3, Magnetic Force, is broken into three subsections: charged particles in a magnetic field, magnetic force on a current-carrying conductor, and galvanometers. What to expect? In this chapter, you will learn that a current-carrying coil of wire behaving like a magnet. You will also study the forces exerted on charged particles that are moving in a magnetic field. Why it matters? Permanent magnets and electromagnets are used in many everyday and scientific applications. Huge electromagnets are used to pick up and move heavy loads, such as scrap iron at a recycling plant. Objectives, Section 1, Magnets and Magnetic Fields. For given situations, predict whether magnets will repel or attract each other. Describe the magnetic field around a permanent magnet. Describe the orientation of Earth's magnetic field. Figure 1, magnets come in a variety of shapes and sizes, but like poles of two magnets always repel one another. Magnets. Most people have had experience with different kinds of magnets, such as those shown in Figure 1. You have probably seen a variety of magnet shapes, such as horseshoe magnets, bar magnets, and the flat magnets frequently used to attach items to a refrigerator. All types of magnets attract iron-containing objects, such as paper clips and nails. In the following discussion, we will assume that the magnet has the shape of a bar. Iron objects are most strongly attracted to the ends of such a magnet. These ends are called poles. One is called the North Pole, the other is called the South Pole. The names derive from the behavior of a magnet on Earth. If a bar magnet is suspended from its midpoint so that it can swing freely in a horizontal plane, it will rotate until its north pole points north and its south pole points south. In fact, a compass is just a magnetized needle that swings freely on a pivot. The list of important technological applications of magnetism is very long. For instance, large electromagnets are used to pick up heavy loads. Magnets are also used in meters, motors, generators, and loudspeakers. Magnetic tapes are routinely used in sound and video recording equipment, and magnetic recording material is used on computer disks. Superconducting magnets are currently being used to contain extremely high temperature plasmas that are used in controlled nuclear fusion research. Superconducting magnets are also used to levitate modern trains. These maglev trains are faster and provide a smoother ride than the ordinary train system because of the absence of friction between the train and the track. Like poles repel each other and unlike poles attract each other. The magnetic force between two magnets can be likened to the electric forces between charged objects in that unlike poles of two magnets attract one another and like poles repel each other. Thus, the north pole of a magnet is attracted to the south pole of another magnet, and two north poles or two south poles brought close together repel each other. Electric charges differ from magnetic poles in that they can be isolated, whereas magnetic poles cannot. In fact, no matter how many times a permanent magnet is cut, each piece always has a north pole and a south pole. Thus, magnetic poles always occur in pairs. Figure 2, when a substance is unmagnetized, its domains are randomly oriented. Magnetic domains. The magnetic properties of many materials are explained in terms of a model in which an electron is said to spin on its axis, much like a top does. This classical description should not be taken literally. The property of electron spin can be understood only with the methods of quantum mechanics. The spinning electron represents a charge that is in motion. As you will learn in the next section of this chapter, moving charges create magnetic fields. In atoms containing many electrons, the electrons usually pair up with their spins opposite each other, causing their fields to cancel each other. For this reason, most substances such as wood and plastic are not magnetic. However, in materials such as iron, cobalt, and nickel, the magnetic fields produced by the electron spins do not cancel completely. Such material are said to be ferromagnetic. In ferromagnetic materials, strong coupling occurs between neighboring atoms to form large groups of atoms whose net spins are aligned. These groups are called magnetic domains. Magnetic domains, a region composed of a group of atoms whose magnetic fields are aligned in the same direction. Domains typically range in size from about 10 to the negative fourth centimeters to 10 to the negative 1 centimeters. In an unmagnetized substance, the domains are randomly oriented, as shown in Figure 2. When an external magnetic field is applied, the orientation of the magnetic field of each domain may change slightly to more closely align with the external magnetic field, or the domains that are already aligned with the external field may grow at the expense of other domains. This alignment enhances the applied magnetic field. Some materials can be made into permanent magnets. Just as two materials such as rubber and wool can become charged after they are rubbed together, an unmagnetized piece of iron can become a permanent magnet by being stroked with a permanent magnet. Magnetism can be induced by other means as well. For example, if a piece of unmagnetized iron is placed near a strong permanent magnet, the piece of iron will eventually become magnetized. The process can be reversed either by heating or cooling the iron, or by hammering the iron, because these actions cause the magnetic domains to jiggle and lose their alignment. A magnetic piece of material is classified as magnetically hard or soft, depending on the extent to which it retains its magnetism. Soft magnetic materials, such as iron, are easily magnetized, but also tend to lose their magnetism easily. In hard magnetic materials, domain alignment persists after the external magnetic field is removed. The result is a permanent magnet. In contrast, hard magnetic materials such as cobalt and nickel are difficult to magnetize, but once they are magnetized, they tend to retain their magnetism. In soft magnetic materials, once the external field is removed, the random motion of the particles in the material changes the orientation of the domains, and the material returns to an unmagnetized state. Figure 3, the magnetic field A of a bar magnet can be traced with a compass B. Note the north poles of the compasses points in the direction of the field lines from the magnet's north pole to its south pole. Magnetic fields. You know that the interaction between charged objects can be described using the concept of electric field. A similar approach can be used to describe the magnetic field that surrounds any magnetized material. Magnetic field, a region in which a magnetic force can be detected. As with an electric field, a magnetic field B, capital B, is a vector quantity that has both magnitude and direction. Magnetic field lines can be drawn with the aid of a compass. The magnetic field of a bar magnet can be explored using a compass, as illustrated in Figure 9. If a small, freely suspended bar magnet, such as the needle of a compass, is brought near a magnetic field, the compass needle will align with the magnetic field lines. The direction of the magnetic field B at any location is defined as the direction that the north pole of the compass needle points to at that location. Magnetic field lines appear to begin at the north pole of a magnet and to end at the south pole of the magnet. However, magnetic field lines have no beginning or end. Rather, they always form a closed loop. In a permanent magnet, the field lines actually continue within the magnet itself to form a closed loop. These lines are not shown in the illustration. This text will follow a simple convention to indicate the direction of B. An arrow will be used to show a magnetic field that is in the same plane as the page, as shown in Table 1. When the field is directed into the page, we will use a series of blue crosses to represent the tails of arrows. If the field is directed out of the page, we will use a series of blue dots to represent the tips of the arrows. Magnetic flux relates to the strength of the magnetic field. One useful way to model magnetic field strength is to define a quantity called magnetic flux. That's phi sub m. It's a Greek letter phi. It is defined as the number of field lines that cross a certain area at right angles to that area. Greek letter phi with a sub m. Magnetic flux can be calculated by the following equation. Magnetic flux phi sub m equals AB cosine theta. Magnetic flux equals surface area times magnetic field component normal to the plane of surface. Now look at figure 3. Imagine two circles of the same size that are perpendicular to the axis of the magnet. One circle is located near one pole of the magnet and the other is alongside the magnet. More magnetic field lines cross the circle that is near the pole of the magnet. The greater flux indicates that the magnetic field is strongest at the magnet's poles. Can you imagine what Earth would be like without a magnetic field? The magnetic field protects the Earth from solar radiation and solar winds. It really is quite powerful. Look up other pictures. This is obviously an artistic rendering, but it's pretty significant. Table 1, conventions for representing the direction of a magnetic field. Look at that drawing very carefully. Figure 4. Earth's magnetic field has a configuration similar to a bar magnet's. Note that the magnetic south pole is near the geographic north pole and that the magnetic north pole is near the geographic south pole. Earth has a magnetic field similar to that of a bar magnet. The north and south poles of a small bar magnet are correctly described as the north-seeking and the south-seeking poles. Let's read at the bottom. This description means that if a magnet is used as a compass, the north pole of the magnet will seek or point to a location near the geographic north pole of Earth. Did you know, by convention, the north pole of a magnet is frequently painted red? This practice comes from the long-standing use of magnets in the form of compasses as navigational aids. Long before global positioning systems, GPS satellites, the compass gave humans an easy way to orient themselves. Because unlike poles attract, we can deduce that the geographic north pole of Earth corresponds to the magnetic south pole, and the geographic south pole of Earth corresponds to the magnetic north pole. Note that the configuration of Earth's magnetic field pictured in figure 4 resembles the field that would be produced if a bar magnet were buried within Earth. If a compass needle is allowed to rotate both perpendicular to and parallel to the surface of Earth, the needle will be exactly parallel with respect to Earth's surface, only near the equator. As the compass is moved northward, the needle will rotate so that it points more toward the surface of Earth. Finally, at a point just north of Hudson Bay in Canada, the north pole of the needle will point directly to Earth's surface. Absolutely fascinating. This site is considered to be the location of the magnetic south pole of Earth. It is approximately 1,500 kilometers from Earth's geographic North Pole. Similarly, the magnetic North Pole of Earth is roughly the same distance from the geographic South Pole. The difference between true north, which is defined as the axis of rotation of the Earth, and north indicates by a compass, varies from point to point on Earth. This difference is referred to as magnetic declination. An imaginary line running roughly north to south through the center of North America currently has zero declination. Along the line, a compass will indicate true north. However, in the state of Washington, a compass aligns about 20 degrees east of true north. To further complicate matters, geological evidence indicates that Earth's magnetic field has changed and even reversed throughout Earth's history. Although Earth has large deposits of iron ore deep beneath its surface, the high temperatures in Earth's liquid core prevent the iron from retaining any permanent magnetization. It is considered more likely that the source of Earth's magnetic field is the movement of the charges in convection currents in Earth's core. These currents occur because the temperature in Earth's liquid core is not evenly distributed. Charged ions or electrons circling in the liquid interior of Earth could produce a magnetic field. There is also evidence that the strength of a planet's magnetic field is related to the planet's rate of rotation. For example, Jupiter rotates at a faster rate than Earth does, and recent space probes indicate that Jupiter's magnetic field is stronger than Earth's is. Conversely, Venus rotates more slowly than Earth does and has been found to have a weaker magnetic field than Earth does. Investigations into the cause of Earth's magnetism continues. Here's a little bit of an anatomy of Earth's magnetic field and how it defends Earth from solar winds. Section review number 1. For each of the cases in the figure below, identify whether the magnets will attract or repel one another. All right, A will repel, B will attract, and C will attract. All right. When you break a bar magnet in half, how many poles does each piece have? It will have 2, and every time you break it in half, it will continue to have 2. Interpreting graphics, which of the compass needle orientations in the figure below might correctly describe the magnet's field at that point? It will be A and B. Critical thinking. Satellite ground operators use the feedback from a device called a magnetometer, which senses the direction of Earth's magnetic field to decide which torque coil to activate. What direction will the magnetometer read for Earth's magnetic field when the satellite passes over Earth's equator? Parallel to Earth's surface, pointing from approximately the geographic South Pole, magnetic North Pole, to approximately the geographic North Pole, magnetic South Pole. Critical thinking. In order to protect other equipment, the body of a satellite must remain unmagnetized even when the torque coils have been activated. Would hard or soft magnetic materials be best for building the rest of the satellite? Hard magnetic material because it is less easily magnetized. Magnetic resonance imaging, or MRI, is an imaging technique that has been used in clinical medicine since the early 1980s. MRI allows doctors to make two-dimensional images or three-dimensional models of parts of the human body. The use of MRI in medicine has grown rapidly. MRI produces high-resolution images that can be tailored to study different types of tissues, depending on the application. Also, MRI procedures are generally much safer than computerized axial tomography, CAT scans, which flood the body with radiation. Here are some images that will help you understand the anatomy and the structure of an MRI and how the machine actually works. A typical MRI machine looks like a giant cube, 2 to 3 meters on each side, with a cylindrical hollow in the center to accommodate the patient, as shown in the illustration. The MRI machine uses electromagnets to create magnetic fields ranging in strength from 0.5 to 2 Teslas. These fields are strong enough to erase credit cards and to pull pens out of your pocket, even across the MRI exam room. Because resistance would cause normal electromagnets to dissipate a huge amount of heat when creating fields this strong, the electromagnets in most MRI machines contain superconducting wires that have zero resistance. Here's some pictures that will help illustrate what is being read here. Very claustrophobic. There are MRI machines that are more open. The creation of an image with MRI depends on the behavior of the atomic nuclei within a magnetic field. In a strong magnetic field, the nucleus of an atom tends to line up along the direction of the field. This behavior is particularly true for hydrogen atoms, which are the most common atoms in the body. The primary magnet in an MRI system creates a strong, uniform magnetic field centered on the part of the patient that is being examined. The field causes hydrogen nuclei in the body to line up in the direction of the field. A most excellent illustrations the use of MRI basic principle. You might want to read this at your leisure. Smaller magnets called gradient magnets are then turned on and off to create small variations or pulses in the overall magnetic field. Each pulse causes the hydrogen nuclei to shift away from their alignment. After the pulse, the nuclei return to alignment, and as they do so, they emit radio frequency electromagnetic waves. Scanners within the MRI machine detect these radio waves, and a computer processes the waves into images. Different types of tissues can be seen with MRI, depending on the frequency and duration of the pulses. Here is an illustration that illustrates what was just read. MRI is particularly good for imaging the brain and spinal tissues and can be used to study brain function, brain tumors, multiple sclerosis, and other neurological disorders. MRI can also be used to create images of blood vessels without the surrounding tissue, which can be very useful for studying the circulatory system. The main drawbacks of MRI are that MRI systems are very expensive and that MRI cannot be used on some patients, such as those with pacemakers or certain types of metal implants. Here's a picture of a MRI. You can see how large it is, mainly because of the magnets that are located inside. Section 2, magnetism from electricity. Describe the magnetic field produced by current in a straight conductor and in a solenoid. Use the right-hand rule to determine the direction of the magnetic field in a current-carrying wire. Figure 5a, when the wire carries a strong current, the alignments of the iron filings show that the magnetic field induced by the current forms concentric circles around the wire. B. Compasses can be used to show the direction of the magnetic field induced by the wire. Absolutely fascinating. Magnetic field of a current-carrying wire. Scientists in the late 1700s suspected that there was a relationship between electricity and magnetism, but no theory had been developed to guide their experiments. In 1820, Danish physicist Hans Christian Ørsted devised a method to study this relationship. Following a lecture to his advanced class, Ørsted demonstrated that when brought near a current-carrying wire, a compass needle is deflected from its usual north-south orientation. He published an account of this discovery in July of 1820, and his work stimulated other scientists all over Europe to repeat the experiment. A long, straight, current-carrying wire has a cylindrical magnetic field. The experiment shown in Figure 5a uses iron filings to show that a current-carrying conductor produces a magnetic field. In a similar experiment, several compass needles are placed in a magnetic plane near a vertical wire, as illustrated in Figure 5b. When no current is in the wire, all needles point in the same direction, that of the Earth's magnetic field. However, when the wire carries a strong, steady current, all the needles deflect in directions tangent to concentric circles around the wire. This result points out the direction of B, the magnetic field induced by the current. When the current is reversed, the needles reverse direction. Figure 6, you can use the right-hand rule to find the direction of this magnetic field. Works like a charm. The right-hand rule can be used to determine the direction of the magnetic field. These observations show that the direction of B is consistent with a simple rule for conventional current known as the right-hand rule. If the wire is grasped in the right hand with the thumb in the direction of the current as shown in Figure 6, the four fingers will curl in the direction of B. As shown in Figure 5a, the lines of B form concentric circles about the wire. By symmetry, the magnitude of B is the same everywhere on the circular path centered on the wire and lying in a plane perpendicular to the wire. Experiments show that B is proportional to the current in the wire and inversely proportional to the distance from the wire. A, the magnetic field of a current loop is similar to B, that of a bar magnet. Study very carefully. Magnetic field of a current loop. The right-hand rule can also be applied to find the direction of the magnetic field of a current-carrying loop, such as the loop represented in Figure 7a. Regardless of where on a loop you apply the right-hand rule, the field within the loop points in the same direction, upward. Note that the field lines of the current carrying loop resemble those of a bar magnet as shown in figure 7b. If a long, straight wire is bent into a coil of several closely spaced loops, as shown in the next page in figure 8, the resulting device is called a solenoid. Solenoid, a helically wound coil of insulated wire. The magnetic field inside a solenoid is strong and nearly uniform. Note that the field lines resemble those of a bar magnet, so a solenoid effectively has north and south poles. Figure 8, visual strategy. Have students practice using the right-hand rule by confirming that the direction of the magnetic field shown in figure 8 is correctly drawn at all points around the solenoid. Point out to students that the fingers curl along the turns of the solenoid. If the current in the solenoid is reversed, which end of the solenoid is the north pole, the right side? Solenoids produce a strong magnetic field by combining several loops. A solenoid is important in many applications because it acts as a magnet when it carries a current. The magnetic field strength inside a solenoid increases with the current and is proportional to the number of coils per unit length. The magnetic field of a solenoid can be increased by inserting an iron rod through the center of the coil. This device is often called an electromagnet. The magnetic field that is induced in the rod adds to the magnetic field of the solenoid, often creating a powerful magnet. Figure 8 shows the magnetic field lines of a solenoid. Note that the field lines inside the solenoid point in the same direction, are nearly parallel, are uniformly spaced, and are close together. This indicates that the field inside the solenoid is strong and nearly uniform. The field outside the solenoid is non-uniform and much weaker than the interior field. Solenoids are used in a wide variety of applications, from most of the appliances in your home to very high precision medical equipment. Section review. Number 1. What is the shape of the magnetic field produced by a straight current carrying wire? A straight current carrying wire. Concentric circles around the wire. Why is the magnetic field inside a solenoid stronger than the magnetic field outside? The fields produced by the top and bottom of every loop all point in the same direction and are confined to a small region of space. If electrons behave like magnets, then why aren't all atoms magnets? That is a good question. Electrons usually pair up with their spins opposite each other, and their fields cancel each other. I'm not sure that's a very satisfactory answer. In some satellites, torque coils are replaced by devices called torque rods. In torque rods, a ferromagnetic material is inserted into the coil. Why does a torque rod have a stronger magnetic field than a torque coil? The magnetic field that is induced by domain variation in the rod adds to the magnetic field of the solenoid. Very interesting. Objective, Section 3, magnetic force. Given the force on a charge in a magnetic field, determine the strength of the magnetic field. Use the right-hand rule to find the direction of the force on a charge moving through a magnetic field. Determine the magnitude and direction of the force on a wire carrying current in a magnetic field. Charged particles in a magnetic field. Although experiments show that a constant magnetic field does not exert a net force on a stationary charged particle, charges moving through a magnetic field do experience a magnetic force. This force has its maximum value when the charge moves perpendicular to the magnetic field, decreases in value at other angles, and becomes zero when the particle moves along the field lines. To keep the math simple in this book, we will limit our discussion to situations in which charges move parallel or perpendicular to the magnetic field lines. A charge moving through a magnetic field experiences a force. Recall that the electric field at a point in space is defined as the electric force per unit charge acting on some test charge placed at that point. In a similar manner, we can describe the properties of the magnetic field, B, in terms of the magnetic force exerted on a test charge at a given point. Our test object is assumed to be a positive charge Q moving with velocity v perpendicular to capital B. It has been found experimentally that the strength of the magnetic force on the particle moving perpendicular to the field is equal to the product of the magnitude of the charge Q, the magnitude of the velocity v, and the strength of the external magnetic field B, as shown by the following relationship. Force magnetic equals QVB, charge, velocity, strength of magnetic field. This expression can be rearranged as follows. Magnitude of a magnetic field, B, capital B, equals force magnetic divided by QV. Magnetic field equals magnetic force on a charged particle divided by magnitude of charge times speed of charge. Thus, if a 1 Coulomb charge moving at 1 meter per second perpendicular to a magnetic field experiences a magnetic force of 1 Newton, the magnitude of the magnetic field is equal to 1 Tesla. Most magnetic fields are much smaller than 1 T. We can express the units of the magnetic field as follows. T, or Tesla, equals Newton over Coulomb dot meter per second equals Newton over area meter equals volt second over meter squared. Figure 9, use this alternative right-hand rule to find the direction of the magnetic force on a positive charge. Conventional laboratory magnets can produce magnetic fields up to about 1.5 Tesla. Superconducting magnets can generate magnetic fields as great as 30 Tesla have been constructed. For comparison, Earth's magnetic field near its surface is about 50 microtesla, 5 times 10 to the negative fifth Tesla. An alternative right-hand rule can be used to find the direction of the magnetic force. Experiments show that the direction of the magnetic force is always perpendicular to both the velocity v and the magnetic field B. To determine the direction of the force, use the right-hand rule. As before, place fingers in the direction of B with your thumb pointing in the direction of V, as illustrated in Figure 9. The magnetic force, F magnetic, on a positive charge is directed out of the palm of your hand. If the charge is negative rather than positive, the force is directed opposite that shown in Figure 9. That is, if Q is negative, simply use the right-hand rule to find the direction of the F magnetic for positive Q, and then reverse this direction for the negative charge. The force on a moving charge due to a magnetic field is used to create pictures on a television screen. The main components of a television is the cathode ray tube, which is essentially a vacuum tube in which electric fields are used to form a beam of electrons. Phosphor on the television screen glows when it is struck by the electrons in the beam. Without magnetism, however, only the center of the screen would be illuminated by the beam. The direction of the beam is changed by two electromagnets, one deflecting the beam horizontally, the other deflecting the beam vertically. In a cathode ray tube, the cathode is a heated filament inside a vacuum tube, similar to the filament in a light bulb. The ray is a stream of electrons that comes off the heated filament into a vacuum. Here is an old television set. This particular why it matters is actually a bit outdated. These are old television sets, the old heavy, clunky cathode ray tube. But you can see that they still exist. They're still used widely, especially in the old computer monitors. But there are newer versions that aren't this big and clunky. The direction of the beam can be changed by changing the direction of the current in each electromagnet. In this way, the beam illuminates the entire screen. In a color television, three different colors of phosphor, red, green, and blue, the primary colors of light, make up the screen. Three electron beams, one for each color, scan over the screen to produce a color picture. Sample problem A. A photon moving east experiences a force of 8.8 times 10 to the negative 19 newtons upward due to Earth's magnetic field. At this location, the field has a magnitude of 5.5 times 10 to the negative 5th Tesla to the north. Find the speed of the particle. Okay, here we go. We'll put the given down, and that's going to be Q. That's the charge of the particle. And then that's B. And F magnetic. The unknown is going to be the velocity. And choose an equation or situation. There's the equation. Use the definition of magnetic field strength. Rearrange, solve for V. There's the rearranged equation. There is the given. I'm going to plug in there and now calculate 1.0 times 10 to the 5th meters per second. The directions given can be used to verify the right-hand rule. Imagine standing at this location and facing north. Turn the palm of your hand upward, the direction of the force, with your thumb pointing east. The direction of the velocity. If your palm and thumb point in these directions, your fingers point directly north in the direction of the magnetic field as they should. A proton moves perpendicularly to a magnetic field that has a magnitude of 4.2 times 10 to the negative second Teslas. What is the speed of the particle if the magnitude of the magnetic force on it is 2.4 times 10 to the negative 14th newtons? There's the equation. There's B. There's F magnetic. There's Q. And there is the rearranged equation set for V. I'm going to plug in and it's going to be 3.57 times 10 to the 6th meters per second. If an electron in an electron beam experiences a downward force of 2.0 times 10 to the negative 14th newtons while traveling in a magnetic field of 8.3 times 10 to the negative second Teslas west, what is the direction of the magnitude of the velocity? Again, here's the equation. It's all rearranged and set. Here's the F magnetic and the value for B and the value for Q. Now we're going to plug in, as we have there, and calculate. 1.5 times 10 to the 6th meters per second north. A uniform 1.5 Tesla magnetic field points north. If an electron moves vertically downward towards the ground with a speed of 2.5 times 10 to the 7th meters per second through this field, what force, magnitude, and direction will act on it? There's the rearranged formula directly. There's the value for B, 1.5 t north. There's the value for V. There's the value for Q. Now we're going to plug in and calculate. Figure 10, when the velocity v of a charged particle is perpendicular to a uniform magnetic field, the particle moves in a circle whose plane is perpendicular to B. Visual strategy figure 10, students should be encouraged to apply the right-hand rule to describe the force on the charge at several points on the circle. What direction would the force on a moving charged particle be if the particle were on the left side of the circle? To the right, toward the center. A charge moving through a magnetic field follows a circular path. Consider a positively charged particle moving in a uniform magnetic field. Suppose the direction of the particle's initial velocity is exactly perpendicular to the field as shown in figure 10. Application of the right-hand rule for the charge Q shows that the direction of the magnetic force, F magnetic, at the charge's location is to the left. Furthermore, application of the right-hand rule at any point shows that the magnetic force is always directed towards the center of the circular path. Therefore, the magnetic force is, in effect, a force that maintains circular motion and changes only the direction of V, not its magnitude. Now consider a charged particle traveling with its initial velocity at some angle to a uniform magnetic field. A component of the particle's initial velocity is parallel to the magnetic field. This parallel part is not affected by the magnetic field, and that part of the motion will remain the same. The perpendicular part results in a circular motion, as described above. The particle will follow a helical path, like the red stripes of a candy cane, whose axis is parallel to the magnetic field. Here are some additional drawings, artistic renderings of the magnetic fields around Earth. Pretty fascinating, actually. Without it, the Earth would fry up like a French fry. Figure 11, a current-carrying conductor in a magnetic field experiences a force that is perpendicular to the direction of the current. Magnetic force on a current-carrying conductor. Recall that current consists of many charged particles in motion. If a force is exerted on a single charged particle when the particle moves through a magnetic field, it should be no surprise that a current carrying wire also experiences a force when it is placed in a magnetic field. The resultant force on the wire is the sum of the individual magnetic forces on the charged particles. The force on the particles is transmitted to the bulk of the wire through collisions with the atoms making up the wire. Consider a straight segment of wire of length L carrying current I in a uniform external magnetic field B, as in figure 11. When the current and magnetic field are perpendicular, the magnitude of the total magnetic field on the wire is given by the following relationship. Force on a current carrying conductor perpendicular to a magnetic field. The force magnetic equals BIL. Magnitude of magnetic force equals magnitude of magnetic field times the current times length of conductor within B. The direction of the magnetic force on the wire can be obtained by using the right-hand rule. However, in this case, you must place your thumb in the direction of the current rather than in the direction of the velocity v. In figure 11, the direction of the magnetic force on the wire is to the left. When the current is either in the direction of the field or opposite the direction of the field, the magnetic force on the wire is zero. Two parallel wires, each carrying a steady current, exert magnetic forces on each other. The force is A, attractive if the currents have the same direction, and B, repulsive if the two currents have opposite directions. Figure 13, in a loudspeaker, when the direction and magnitude of the current in the coil of wire change, the paper cone attached to the coil moves, producing sound waves. Two parallel conducting wires exert a force on one another. Because a current in a conductor creates its own magnetic field, it is easy to understand that two current-carrying wires placed close together exert magnetic forces on each other. When the two conductors are parallel to each other, the direction of the magnetic field created by one is perpendicular to the direction of the current of the other, and vice versa. In this way, the force of F magnetic equals BIL acts on each wire, where B is the magnitude of the magnetic field created by the other wire. Consider the two long, straight, parallel wires shown in figure 12. When the current in each is the same direction, the two wires attract one another. Confirm this by using the right-hand rule. Put your thumb in the direction of the current in one wire and point your fingers in the direction of the field produced by the other wire. By doing this, you find that the direction of the force pointing out of the palm of your hand is towards the other wire. When the currents in each wire are in opposite directions, the wires repel one another. Loudspeakers use magnetic force to produce sound. The loudspeakers in most sound systems use a magnetic force acting on a current-carrying wire in a magnetic field to produce sound waves. One speaker design, shown in figure 13, consists of a coil of wire, a flexible paper cone attached to the coil that acts as the speaker, and a permanent magnet. In a speaker system, a sound signal is converted to a varying electric signal by the microphone. This electrical signal is amplified and sent to the loudspeaker. At the loudspeaker, this varying electrical current causes a varying magnetic force on the coil. This alternating force on the coil results in vibrations of the attached cone, which produce variations in the density of the air in front of it. In this way, an electric signal is converted to a sound wave that closely resembles the sound wave produced by the source. Problem, sample problem A. A wire 36 meters long carries a current of 22 amps from east to west. If the magnetic force on the wire due to Earth's magnetic field is downward towards Earth and has a magnitude of 4 times 10 to the negative 2 newtons, find the magnitude and direction of the magnetic field at this location. Given. It's going to run this right out. The length is 36 meters. That's the length of the wire. I is 22 amps. There's the force magnetic. The unknown is B. Choose an equation or situation. Use the equation for the force on a current-carrying conductor perpendicular to a magnetic field. All right, so we'll use that equation. There it is. Rearrange to solve for B. All right. Bring that forward, list given, and then plug in, solve, and now we will interpret. Using the right-hand rule to find the direction of B, face north with your thumb pointing to the west in the direction of the current and the palm of your hand down in the direction of the force. Your fingers point north. Thus, Earth's magnetic field is from south to north. Number 1, a 6-meter wire carries a current of 7 amps towards the plus X direction. A magnetic force of 7 times 10 to the negative 6 newtons acts on the wire in the negative Y direction. Find the magnitude and direction of the magnetic field producing the force. All right, there is the equation. Very good. There's L, I, force magnetic, and the answer. Okay. Number 2, a wire 1 meter long experiences a magnetic force of 0.5 newtons due to a perpendicular uniform magnetic field. If the wire carries a current of 10 amps, what is the magnitude of the magnetic field? There's the equation to solve for B. There's the given. Now we're going to plug in and solve. 0.050 Teslas. The magnetic force on a straight 0.15 meter segment of wire carrying a current of 4.5 amps is 1 newton. What is the magnitude of the component of the magnetic field that is perpendicular to the wire? There's the equation for B. I went to the magnitude of the component of the magnetic field. So here is the given quantities. And I'm going to plug in and I'm going to solve. All right. The magnetic force acting on a wire that is perpendicular to a 1.5 Tesla uniform magnetic field is 4.4 newtons. If the current in the wire is 5 amps, what is the length of the wire that is inside the magnetic field. All right, I already gave the equation, although we're going to rearrange it. We're going to list the given, and we are going to plug in and solve. 0.59 meters. Figure 14, in a galvanometer, when current enters the coil, which is in a magnetic field, the magnetic force causes the coil to twist. Figure 14, visual strategy. Encourage students to use the right-hand rule to understand how a galvanometer works. If charges move through the coil from left terminal to the right terminal, which direction will the needle rotate? Clockwise. Okay. A galvanometer is a device used in the construction of both ammeters and voltmeters. Its operation is based on the fact that a torque acts on a current loop in the presence of a magnetic field. Figure 14 shows a simplified arrangement of the main components of a galvanometer. It consists of a coil of wire wrapped around a soft iron core, mounted so that it is free to pivot in the magnetic field provided by the permanent magnet. The torque experienced by the coil is proportional to the current in the coil. This means that the larger the current, the greater the torque, and the more the coil will rotate before the spring tightens enough to stop the movement. A galvanometer. Hence, the amount of deflection of the needle is proportional to the current in the coil. When there is no current in the coil, the spring returns the needle to zero. Once the instrument is properly calibrated, it can be used in conjunction with other circuit elements as an ammeter to measure currents, or as a voltmeter to measure potential differences. Section review, number 1. A particle with a charge of 0.03 coulombs experiences a magnetic force of 1.5 newtons while moving at right angles to a uniform magnetic field. If the speed of the charge is 620 meters per second, what is the magnitude of the magnetic field the particle passes through? All right, good. There's the equation, and there's the charge. There's the F magnetic, the velocity. I'm going to plug in, and I'm going to calculate 0.081 Teslas. An electron moves north, encounters a uniform magnetic field. If the magnetic field points east, what is the direction of the magnetic force on the electron? Upward. A straight segment of a wire has a length of 25 centimeters and carries a current of 5 amps. If the wire is perpendicular to the magnetic field of 0.6 Teslas, then what is the magnitude of the magnetic force on this segment of the wire? F magnetic equals BIL. There's L, there's I, there's B, plug in, calculate, 0.75 newtons. Two parallel wires have charges moving in the same direction. Is the force between them attractive or repulsive. Attractive. Find the direction of the magnetic force on the current carrying wire in figure 15. Out of the page. Section 1, Key Ideas, Magnets and Magnetic Fields. Like magnetic poles repel, and unlike poles attract. A magnetic domain is a group of atoms whose magnetic fields are aligned. The direction of any magnetic field is defined as the direction the north pole of a magnet would point if placed in the field. The magnetic field of a magnet points from the north pole of the magnet to the south pole. The magnetic north pole of Earth corresponds to the geographical south pole, and the magnetic south pole corresponds to the geographic north pole. Section 2. A magnetic field exists around any current-carrying wire. The direction of the magnetic field follows a circular path around the wire. The magnetic field created by a solenoid or coil is similar to the magnetic field of a permanent magnet. Section 3, Magnetic Force. The direction of the force on a positive charge moving through a magnetic field can be found by using the alternate right-hand rule. A current-carrying wire in an external magnetic field undergoes a magnetic force. The direction of the magnetic force on the wire can be found by using the alternate right-hand rule. Two parallel current-carrying wires exert on one another forces that are equal in magnitude and opposite in direction. If the currents are in the same direction, the two wires attract one another. If the currents are in opposite directions, the wires repel one another. The end. Have a nice day.